Hello, IME 146 students. Welcome to week number 3, where we're going to talk about injection molding, and then we're going to go ahead and injection mold our Geneva wheel handles out in the lab and use the lathes to go ahead and face, drill, and tap the thread in the part, and then check for runout. So you're going to learn about runout with GD&T and about injection molding. At the same time in lab, you're also going to learn about single point threading and creating threads using the lathe. So I know some of you actually emailed me with some questions about creating threads on the lathe. Now you'll actually get to do it. I didn't get a chance to get back to you on your email, and I'm sorry. I think you know who you are if you're watching this video. But you'll get to do that this week in lab, and you'll go ahead and set the thread pitch to the feed rate, or actually you'll set the feed rate on the lathe to the thread pitch, and then make an actual thread using the lathe and a single point cutting tool. But let's first talk about injection molding. And you'll have the weekly timed lab quiz on the injection molding. But remember, you can take that as many times as you want and get the average of the score. But out there, when we have polymers, we have 3 different types of polymers. We have thermoplastics, which can heat up, and basically we can injection mold them into a mold. When they cool down, they solidify in that shape. And the thing about thermoplastics, though, is we can go ahead and chop them up and recycle them and heat them up again, remelt them, and reuse them. So thermoplastics are able to be remelted over and over. That's a little bit different than a different type of polymer called a thermoset. What thermoset polymers do is they cross-link. Like a bowling ball, you can't melt a bowling ball because it's been polymerized. It polymerizes and it cross-links when it goes ahead and it gets formed during manufacturing. So it sets up, and once it sets up in that shape, you can't really remelt it. It basically burns or chars afterwards. And that's what a thermoset polymer is all about. Now, more elastomers are more like rubbers or bushings, stuff like that. They're actually formed with a liquid, and that polymerizes and solidifies into a polymer. So you usually pour an elastomer into some sort of mold, and then it forms into its shape, and you remove it from that actual mold. What we're going to talk about is injection molding, and about 80 to 90% of the polymer parts out there, thermoplastic parts, are injection molded. So thermoplastics are injection molded. Thermosets get reaction injection molded. It's a slightly different process. But actually, injection molding started in the late 1800s when there was a contest for a billiard ball company They offered $10,000 to come up with a replacement for an ivory pool ball. So John and his brother Isaiah Hyatt basically they came up with a cellulose formula, a polymer formula, and they invented a machine to inject it into a ball shape, into like a pool ball shape. So they invented primitive injection molding, just trying to make a replacement pool ball. And they didn't win the prize, but they came up with a manufacturing process. Their machine basically uses a plunger that heated up material, and it plunges it through a nozzle into an actual mold. Now, in the 1940s, in 1946, James Henry went ahead and invented the screw-style injection molding machine, and that's what you're going to see more so today in the production shops out there is a screw-style machine. We have an actual plunger-style machine, so it takes a while for it to go ahead and melt. And so in between, our cycle time isn't going to be quick like you would have with the screw-style machine. Let's check out this video right here on injection molding, and we're going to learn more about injection molding part design as we go throughout today's lecture. So check this one out.
Toys, cases for consumer electronics, disposable cutlery, and my favorite, Lego bricks. Injection molding was invented to solve a problem for billiards. In the 19th century, billiard balls were composed of ivory harvested from the tusks of African elephants. This devastated the elephant population, so a billiards manufacturer offered a $10,000 prize for a replacement for ivory. And this spurred John Wesley Hyatt to develop one of the first plastics, celluloid, to create billiard balls. He patented an apparatus for molding products from celluloid. This apparatus was the birth of plastic injection molding. In principle, injection molding is simple. Melt plastic, inject it into a mold, let it cool, and then out pops a plastic product. In reality, injection molding is an intricate and complex process. An injection molding machine has 3 main parts: the injection unit, the mold, and the clamp. Plastic pellets in the hopper feed into the barrel of the injection unit. Inside the barrel, a screw transports the pellets forward. Heater bands wrapped around the barrel warm up the plastic pellets. As the pellets are moved forward by the screw, they gradually melt and are entirely molten by the time they reach the front of the barrel. Once enough molten plastic is in front of the screw, it rams forward like the plunger of a syringe. In a matter of seconds, the screw injects the molten plastic into the empty part of the mold called the cavity image. The plastic solidifies in under a minute. The mold opens and the part is ejected. The mold then closes and the process repeats. All injection molded objects start with these plastic pellets, which are a few millimeters in diameter. They can be mixed with small amounts of pigment called colorant, or with up to 15% recycled material, then fed into the injection molding machine. Before the mid-20th century, injection molding machines used only external heating of the barrel to melt the plastic before.
So our machine is going to be a lot like the machine he's describing right now. So we have slow cycle times and poor melt.
A plunger injected the molten material. But because plastic conducts heat poorly, the temperature was uneven in the barrel. Either the middle was too cool and not fully melted, or the outer regions were too hot and degraded the plastic. The solution was this: the reciprocating screw, often regarded as the most important contribution that revolutionized the plastics industry in the 20th century. In the earlier plunger-style machines, plastic filled completely the cylindrical barrel. But as I showed you, the plastic was not at a uniform temperature. The reciprocating screw overcomes this in three ways. First, in modern units, the plastic fills only the space around the shaft of the screw. This eliminates the cooler central region, leaving a thinner, evenly heated layer of plastic. Second, the screw has flights that wrap around the shaft. As the screw rotates, the flights transport the raw material forward through the barrel. The flights also serve to mix the plastic. The screw action agitates the melting pellets within the flights to create a uniform mixture. And third, the screw action itself heats the plastic throughout. The shaft's diameter increases along the screw so that the distance between the wall and the shaft decreases. The flights then squeeze out air as they move the plastic forward, and they shear the pellets and press them against the barrel's wall. This shearing creates friction and so heats the plastic throughout. This screw-induced shear supplies a majority of the heat needed to melt the plastic, between 60 and 90%, with the rest from the heater bands. The molten plastic flows past the front of the screw through indentations or flutes. When there's enough plastic to fill the mold at the front of the screw, it rams forward like a plunger, injecting the plastic into the mold. The plastic cannot flow backwards because when the screw pushes forward, a check ring is shoved against a thrust ring to block the backwards movement of the molten plastic. This forces the plastic into the mold. Initially, the cavity image is filled with air. As the molten plastic is injected, it forces air out of the mold, which escapes through vents. These vents are channels ground into the landing surface of the mold. They're very shallow, between 5 and 40 microns deep. The plastic, which has the consistency of warm honey, is too viscous to flow through the narrow vents. To speed the plastic solidification, coolant, typically water, flows through channels inside the mold just beneath the surface of the interior. After the injected part solidifies, the mold opens. As the mold opens, the volume increases without introducing air, which creates tremendous suction that holds the mold together. So at first, the mold slowly opens several millimeters to allow air to rush in and break the vacuum, and then the mold quickly opens the rest of the way so the part can be removed. These precision machined steel molds can cost hundreds of thousands of dollars. Removing the part from the mold can be difficult. When the plastic cools, it shrinks and so becomes stuck tightly on the core half of the mold. Molds have built-in ejector pins that push the part off the mold. The ends of the pins sit.
We don't have ejector pins in our mold setup, so we're going to have to pull our parts out of the mold. Some of them will fall out, some of them you'll have to pull out.
Flush with the core half of the mold, but are not perfectly aligned. Sometimes they protrude or are indented slightly. So if you look closely, you will see circular ejector pin witness marks.
Start looking at plastic parts. You're going to see the witness marks, the parting lines where it gated in. Just start looking at them.
On molded products. For example, this chair on its bottom has an array of witness marks. When the part drops from the mold, an operator has to remove the sprue, that section of plastic that connected the injection unit to the mold. Sprues are manually twisted or cut off the part. Sprues are attached to objects only in molds that make a single part at a time, like a chair. Smaller objects are made in multiples in a single mold. In these, the sprue connects not to the part itself, but to a network of distribution tunnels called runners. The runners fan out from the sprue and connect to each cavity in the mold via a small, typically rectangular, entrance called the gate. You can see the gate on plastic cutlery. The parts for model planes typically come still attached to their runners. Molds always have at least two parts, and where the parts of the mold meet is called the parting line. Here on this piece of cutlery, you see the parting line along the side of the fork. When mold halves close, they are never perfectly aligned, nor do they have sharp corners. This creates a noticeable parting line on the molded object. Another very important aspect of mold design is the draft angle. If a part has walls that are exactly 90 degrees, it will be very difficult to eject because its inner walls will scrape the core half of the mold. Also, the vacuum will be difficult to break because air cannot readily enter. However, if the walls are slightly tapered, even just 1 or 2 degrees, it becomes much easier for the part to be removed because once the part moves slightly, the walls are no longer in contact with the core half and air can rush in. One impressive example of injection molding is the Lego brick. You can see the injection point in the middle of a stud, but this is not from a gate or a sprue. The Lego molds use hot runners. Hot runners are a heated distribution network. This keeps plastic inside the runners molten while the plastic in the mold solidifies. This leaves no gates or sprues to be removed. The molded bricks are ejected, ready to use. The downside is that this setup is more expensive than a traditional cold runner system. On the bottom edge of the brick, you can see ejector pin witness marks. And what's most clever to me is where Lego designs their draft angle. The outside of a Lego brick must be square. So if you cut a Lego brick in half, you can see that these inner supports are thicker at the top than at the bottom. There's a draft angle of about 1.5 degrees. This helps the ejector pins push the brick off the mold. The core half and the cavity half of Lego molds are designed so that the parting line is at the bottom edge of the brick. This hides the parting line. Look around you and see how many injection molded objects you can find. Likely the device you're watching this on has injected molded parts. You should be able to find ejector pin witness marks and parting lines, but you may find something like this. It's a date wheel that shows the month and year the item was made. These are created by removable inserts and can be changed out for each run of the mold. They're very useful for tracking down defects. So to return to where this all started, John Wesley Hyatt and his injection molded billiard ball did not win the $10,000 prize. His celluloid billiard balls didn't bounce quite right. But he did pioneer plastic injection molding, a thriving, continually evolving manufacturing process which creates many billions of products every year. I'm Bill Hammack, the Engineer Guy. To learn more, click on this video overview of injection.
All right, so go back to sharing. So as you can see, the process pretty much starts off with closed machine molds. So we talked about CNC machining last week. We have to start off with a machine mold. And the molds are made out of aluminum. So let me grab an example real quick right here. And right here. So we basically just start off with a set of aluminum blocks right here, and we machine the cavity into it, like you'll see, like you're going to see in a lab. Now, once we have that machine mold, it attaches to the machine. The plastic basically gets injected into that mold. It solidifies, the molds open up, and we have our product. So it's pretty quick process. It lends itself very well to automation because with ejector pins and being able to pop the parts out of the mold automatically, we can pretty much just time that machine to cycle correctly, and we have an automatic molding process occurring. Now, the machine that you're going to use doesn't lend itself very well to automatic molding. It's it's called a Morgan press. It's made in Long Beach, California, and the design really hasn't changed much since 1985. So with this Morgan press, you're going to see that the top up here, let me grab my pen tool, draw on this thing. Right up here is where we load the material. Let me circle right there. And we load up the material into that chute. We close this little gate. There's a little safety switch up there. So if it's not cycling, you might not have closed this gate up here when you loaded your material. But back to this, you load the material, you select your temperatures over here. So the barrel and the nozzle temperature are right there. And we'll talk a little bit about that coming up here. Once you have the material melted, your mold goes down here, and you basically click on this button right here to clamp the machine. It's a toggle button. You either clamp it or you open it, one of the two. So you clamp the machine, and once it's clamped, the material is ready to inject. You push this button right over here, and you inject the material into your actual part. Now, we're going to pretty much level out the injection pressure and the clamping pressure, or we're going to have more clamping pressure than injection pressure. We're going to talk about that coming up. So you shouldn't get a lot of flash if the machine is set up correctly. So you're going to learn how to operate this in lab. You're going to operate this machine in teams of 2, and you're going to end up, team of 2 is going to end up injecting basically a set of Geneva handles like you see right here. You're then going to take those, there's a routing for this, and you're going to go through the machine shop, and you're going to put the threads in the back of the handle so we can attach it to the actual Geneva drive, or the Geneva drive wheel that we machined last week using a screw here through the backside. Now, you're going to see that there's rules for injection molding. So if you're an engineer designing a part and you have to come up with the size of an injection molding machine you need, for example, if you're going to injection mold a trash can, like picks up the trash from your house, or maybe even just a small office trash can, you got to know what your shot size is in your machine. I believe our shot size is 6 ounces for our Morgan press, but the rules for injection molding is you never really want to empty more than 50% of the barrel during the cycle. 50% is ideal, never less than 20, or no greater than 80, because you need time for that material to melt. You want to introduce the non-melted material to some of the material that's already been melted. It's going to allow it to have a quicker cycle time. If you have to wait for virgin material to sit there and melt, it's going to take a long time in order to make your parts. So that's kind of your sizing for your machine versus your part size right there. Usually 50% of the shot size is ideal when you're sizing a machine. And that's including all of your sprues, your gating system, and your runner. That is included in the shot size right there. Now, the barrel is going to be the chamber basically where we melt our material. So what we have is we have a plunger for our barrel. But if you saw the video, most machines are basically are a screw. So there's heater bands connected to that barrel. And all it is an electric heater band, and there's something called a thermocouple. A thermocouple is a temperature sensor. It sends the temperature signal back to a little computer that either turns on the heater band or turns it off right there. So heaters basically control the barrel temperature, and there's basically heat from the shear stress going on in that screw. As the screw augers the material forward, a little bit of shear stress creates the heat as well. Now, the material is basically placed in the hopper or in hoppers. We have a material chute, but larger machines need a big hopper to hold on to the material if they're going to be automatically molding throughout the day. And the thing with material is, like nylon, it likes to absorb moisture. So what we like to do is we like to dry our material in the hopper. So if you look up here towards the right, we have a dryer attached to that hopper. So usually they basically blow air over the material before it goes down into the machine to dry it out there. We don't actually have a dryer, so we may have some steam occurring in some of our material because it's been sitting out there throughout this rainy season we've had here in San Luis Obispo. But realize the hopper is really where we add the material, and this is where you would add the color. So you add the colorant, you add the material, you add the regular beads, and any type of recycled material here. You don't want to add too much recycled material because you'll lose some of the properties in your actual plastic. So what you can see right here is the screw. So we have the injection molding screw right here for a traditional machine, and you'll see the pitch actually changes. There's different zones. There's a feeding zone where it's feeding it forward. It's got a little bit more area there. There's a transition zone where it starts to melt. And then the metering zone is at the front where it's pretty much melted. And that's where it's going to actually plunge it in. So the screw gets it there, but it still kind of plunges it into the actual mold through a nozzle. So there is basically a sprue bushing on the mold. So the mold has a concave radius on it. And that concave radius, you can kind of see it right up here, attaches to the injection molding machine. And there's a nozzle on that machine that goes to that sprue bushing. And that's what creates the pressure in order to clamp the mold and inject the material into the actual mold. Now, the press that we have has 12,000 PSI injection pressure. So we can inject liquid or molten plastic or molten polymers into molds up to 12,000 PSI. Normal practice is to begin molding around 7,000 or 8,000. I think ours actually is a very simple mold, and I think we're around 6,000 PSI. Don't write that down for a homework answer. Go ahead and watch the video and watch the lab demos in order to know your actual numbers there. Now, the clamping unit is going to be how we keep our molds shut. So if we're injecting up to 12,000 PSI molten polymer into a mold cavity, we got to make sure that mold stays shut. So we can have up to 20 tons of clamping force, basically. So it should be clamping force. That's a mistake right there on the slide. It's not clamping pressure. But we have 20 tons of clamping force to hold that mold together and at 200 PSI shop air. We don't have 200 PSI shop air. We have about 120 PSI shop air. So we only have about 12 tons of clamping force there. Now, you actually have to calculate your clamping force versus your injection pressure to make sure that you have enough force to keep the mold closed when you're injecting when you're plastic injection molding. So they have different flow rates and different types of materials. We have a very low flow material out there. So we would have to multiply our cross-sectional area of our mold by about 8 tons per inch squared. And that's how we come up with our clamping pressure right there, our clamping force there. So 8 tons per square inch for our low flow material. And we calculate at the parting line, we calculate what our cross-sectional area is, and that's what we set our actual force at, or clamping force at. Plus, we add a little bit of a safety factor to that calculation there. Now that clamping unit on large machines, if you look, is a large hydraulic piston. But what we have is we have a knuckle joint. And you need to be very careful because when you're cycling this machine, there's really no finger guards for that knuckle joint. It could squish your finger or take a finger off. So keep your fingers out of the way of the bottom of the press when you're operating the clamping unit there. Now, what we have here is we have too much clamping force. We can destroy the molds. If we use too little of a clamping force, the mold might not stay closed and we'll have some flash on the parts, and we'll have issues with the parts because flash on the outside of the part means we have a bad part and we have to keep molding there. So that clamping unit definitely needs, the clamping forces definitely need to go ahead and get calculated on all injection molding processes. Luckily, we've done that for you in lab. For this lab, this is kind of just show you how everything works for injection molding. If you're interested in designing tooling for it, you can take IME 330 and also IME 450, which are required in the manufacturing concentration. But anyways, back to temperature. We're going to set the temperature of the material right at the nozzle, right at the melting temperature of the material. So I'm kind of got mixed up there. So the melting temperature of the material is going to be, we looked that up. It's like right around 590, 585 degrees. We're going to set the nozzle temperature there, but not the barrel temperature. We get the barrel temperature about 10 degrees below the melting temperature of the material. Then we melt it right at the nozzle. And we determine this by doing an air shot. So we'll shoot some polymer out into a little puddle and throw a temperature probe in it and measure the temperature of the plastic melt. So on our Morgan press, we set the barrel temperature and the nozzle temperature and look at the exact temperatures you set them up in lab. I believe it's going to be 580 and 590, right around there. It could be up to about 600 on the nozzle temperature to inject there. Now, we also keep the mold hot. You saw in the video they cool their molds. We don't mold quick enough to need coolant. We have to keep our mold warm because it's made out of aluminum. If we were to inject 500 or 600 degree nylon into a cold mold, it would go ahead and solidify instantly and not fully fill the mold. So we're going to go ahead and use that hot plate controller to warm up the mold to about 200 degrees Fahrenheit before we injection mold there. And that keeps our mold at a constant 200-degree temperature throughout the day, throughout molding. So technically, we're keeping it cooler than the melting temperature, but we're warming up our mold in this case. Bigger machines have cooling jackets and they keep it at a constant, steady temperature as well. Now, if we had too much injection pressure and we didn't have enough clamping force on our molds, we're going to get flash around the parting line. Flash can ruin your molds. If you flash too many times, you can actually flex the mold and damage the mold by having the flash. Basically, you're basically having a fluid flow over through a surface, basically and you're deforming the mold. So you're getting a thin layer of plastic around the outside of the mold cavity where the two halves of the molds meet. Flash is a very bad thing. So that's why we also have to control our injection and our clamping pressures and make sure that they're in line with each other. Now, injection pressures also cause short shots if you set them too low. So you don't want to go ahead and do too low of an injection pressure because you can't fully fill that mold and hold while it solidifies. So you can see right there, we didn't fully make a Lego brick because we didn't have enough injection pressure. Now, when we're doing a cycle time on our mold, you're going to see that's an old set of Geneva handle molds down there in the bottom left. That's when we did 6 at a time. We redesigned the molds to do 2 at a time, and we made it so it flashes a lot less. Those thinner molds that you see down there were flexing, and they were basically causing a lot of flash. So we basically made our molds out of 1-inch thick aluminum. That was 3/4 inch thick aluminum down there. So nevertheless, the cycle time now, it's going to be included in while you're injection molding lab. You got to go ahead and close the mold. I would put a little bit of mold release in the mold before you close it. So spray some of that silicone mold release up in the sprue, close your mold, you push down on the injection button and you inject, you hold down on that injection button for a little bit of time until you feel it kick back on you. When it kicks back, it's pretty much ready. It's ready to stop injecting. You let go of the button. You then allow it to cool for a second or two, maybe like 5 seconds. And then you open the mold by pulling on the unclamp button. Once you unclamp the mold, you basically have to remove the part. It opens up. You remove the part. You push on the side button on the machine to return the plunger back to the top. You make sure you got material, and then you can basically do the process again. So that's kind of the cycle time, or that's what the cycle time includes right there. So there's a lot of different variables you're going to do in order to mold basically two little handles per shot, like right there. Now, we're going to end today's lecture on a little bit of injection molding part design and why we need some of these features here. So a lot of times you can actually mold stresses into injection molded parts by bad part design. Well, number one thing you need is you need draft. You saw in the video, draft allows the part to be removed from the mold. It allows air to enter the mold into that cavity and the part to escape. When I have round parts like this handle right here, it does not need draft on the round edges because it's a curved surface. It pretty much has draft all the way down to that tangent edge on the side where the parting line is. So round parts don't need draft, but vertical wall parts definitely do. And that's why parts like this mouse and so forth, if you look at them, they're designed to be easily molded. So if you look, none of your injection molded parts, except for like Lego bricks on the outside, have basically vertical walls. So when you're designing a part to be injection molded, you want about 1 to 3 degrees of basically draft on that actual part. So you're going to learning about SolidWorks right now. There's a draft tool in SolidWorks to make drafted walls for parts for injection molding. That's one of the uses for it. Now, also, you never design sharp corners. Sharp corners cause stress risers on polymer parts. They'll cause the part to tear. It's really hard to machine a mold with sharp corners as well. So you usually have corner radii or fillet radii on all corners of your injection molded parts. Nice, smooth, and round. Yes, you can get square corners by using EDM, electronic discharge machining, to machine your molds, but you're going to cause probably stress risers in the part. Unless it needs to be perfectly sharp, do not make sharp corners in your injection molded parts. Put fillets in there and radii and so forth. Now, when you're designing a mold or tooling for the part, you always want to gate in or basically fill the mold in the thickest cross section. So you always fill in the thickest cross section, and that helps with cooling and the solidification of the actual part right there. So always gate into the thickest cross section. And we're really just gating in to the thick center of the part. The reason I didn't gate into the top, I wanted the top to be real smooth on the part. So we're gating into this backside where we're going to face that off and drill that off and basically drill and tap that side of the part. So you'll never even see where the gate was on this part. Now, technically, wall thickness, this is very close to standard wall thickness, but this isn't the best design for an injection molded part. It's a solid design. So this is technically bad design. It's going to take a while to solidify and mold. Technically, I should go ahead and core out the handle. That's going to make a very complex mold that we don't have the tooling here at Cal Poly to manufacture in-house. We would have to send it out to an EDM shop to get the mold made with a different manufacturing process. So we sacrificed thin wall thicknesses for our design for manufacturing here at Cal Poly for this mold design. But looking at the parts below there, when you have really thick parts, they get sink. Ours don't have sink. Don't worry about that part. They're not that large to where they're going to sink here. They're going to have nice directional solidification, and we'll be good to go there. But looking at the bottom there, on the bottom left, you can see this part will sink and it can warp because you have a large mass of plastic in one zone and then a really thin mass of plastic in the other. So the thin part's going to solidify at one point. The thick part's going to take a lot longer, and it's going to move around and change size when the thin part's already solidified. You're going to have a warped part and most likely sink on the actual surfaces. Sink just means the surface is sunk when it's solidified, because all the material kind of shrunk down and caused that surface to sink down. So what you would do to solve that is you would core out your geometry like you see right down here. So we got cored out geometry there. You can kind of see this example here, this core geometry, thin walls, the same wall thickness throughout the entire part, or as uniform as possible, is what's another important design tool in injection molding. And you don't want sharp transitions. If you look right here on this part, you wouldn't go from one thickness to the other. You would want to make it a nice smooth chamfer transition. So you're going from one thickness to the other smoothly, because you'll get sink and you'll get a lot of warpage that way. So that's a little bit about injection molding part design. Let's watch the injection molded handles get made real quick in this virtual lab video. In fact, we made this during COVID back in the day. So this video is from quite a while ago, back from when we made COVID. Let me go, or when we made all these virtually. Let me stop real quick. See if my computer's actually going to load that one. We might just have you watch that one in lab. Actually, no, we'll watch it real quick here. Let me jump over to this. Screen share it real quick. I'm having Zoom issues today.
Injection molding is a manufacturing process for producing parts by injecting molten material into a mold. We will begin by operating a small prototype Morgan Press injection molder located in the lab. This injection molder will be used to make the rotary handle in the Geneva wheel class project. We will need two forms of personal protective equipment when operating the injection molder: safety glasses and gloves. Remember that the nozzle, the mold, and the injection molded part will be hot. We'll start by taking an overall look at the Morgan Press injection molding machine. Here we have the main control panel, the toggle clamp linkage, the temperature data chart, mold preheating plate, the mold itself, the injection nozzle, which mates to the mold sprue, the table guard, the clamp force and injection pressure gauges, the material loading chute, the toggle clamp height adjustment, and finally, the ram power return. This is the mold we will be using. It is a multi-part mold with 6 cavities to make 6 handles per properly
Remember, we have a 2-cavity mold, different mold. This is a really old one.
executed injection event. Note the alignment pins in the mold. These pins ensure that the mold bottom and top align correctly when clamped. The runners distribute the material to each mold cavity from the sprue. The sprue is located on the top half of the mold. This is where the nozzle will inject the thermoplastic into the mold. Let's take a closer look at the control panel. First, we have the clamp control knob. The clamp control knob controls the raising and lowering of the mold plate. The safety latch needs to be rotated out of the way before use. Pushing the knob in will clamp the mold, while pulling the knob back will unclamp the mold. Let's watch as we activate and deactivate the clamp control knob.
This is where you have to watch your fingers, keep them out of the way.
To the right is the clamp force selector, which regulates the air pressure to the clamp control valve. This controls the mold's clamp force. The amount of clamp force can be seen on this gauge at the top of the machine.
We're maxed out
Next
there at
is
12
the cycle
tons.
timer knob. This knob is used to limit the amount of injection time. The pilot pressure selector regulates the air pressure to the injection control valve. This controls the injection pressure. The injection pressure can be seen on this gauge at the top of the machine. On the far right is the injection control knob. The injection control knob controls the raising and lowering of the piston, which causes an injection event. The safety latch needs to be rotated out of the way before use. Pushing the knob in will begin an injection event, while pulling the knob back will end the injection event. Around the corner on the right is the ram return knob. Pushing this knob intermittently will return the piston back to the top of its stroke. This is only necessary if the piston does not return on its own after an injection event. To ensure that the mold clamps properly, the height of the clamping table will need to be set so that the clamping linkage goes fully over center at the end of the clamp stroke. The material loading chute is where the plastic pellets will be inserted. These pellets will be melted down and injected into our mold. The material loading chute gate will need to be closed in order to inject material into the mold. There's a chart located on the front of the machine which has suggested temperature settings for different thermoplastics. The settings are a good starting point, but may need to be modified based on the specific material being used. We will be using high impact nylon for our Geneva wheel handles. These settings are denoted by the red star. The mold preheat plate keeps the mold warm. This prevents the thermoplastic from solidifying too early due to being injected into a mold with a large temperature differential. Here, we have the mold preheater set to 200 degrees Fahrenheit. Here the barrel zone temperature controller is shown on the top, while the nozzle zone temperature controller is shown on the bottom. The numbers in red are the current temperature, while the numbers in green are the set temperature. You can see that in this current photo, the barrel and the nozzle are still heating up to temperature. In the new photo, we can see that the barrel and nozzle are up to temperature.
So we're doing
and ready for
590,
injection.
580 for this video example.
Since nylon tends to absorb moisture from the air, we bake the nylon pellets at above the boiling temperature of water to rid the nylon of any absorbed moisture. Here, we load the hopper or material chute with the nylon pellets. We need to make sure to shut the material chute gate before injecting the thermoplastic into the mold. It It will take some time for the material to heat up in the injection barrel. For this particular part and material, somewhere around 2 to 3 minutes is appropriate. We will need to wait this time after every 1 to 2 injection cycles. Here we go through our first injection event. It is common for the first couple of injection events to produce less than perfect parts. There may be some leftover material in the barrel, which has become contaminated or absorbed moisture from the air. We need to make sure that the mold guard is pulled down over the mold table completely, or the injection molder will not function. We now clamp the mold table by pushing the orange clamp control knob. After the mold table rises and the clamp linkage snaps over center, we are ready to inject the thermoplastic. We press the black injection control knob and hold it until the injection is complete, then pull it back into the neutral position. We wait a second or two until we pull the orange clamp control knob to unclamp the mold. We use needle nose pliers to carefully remove the hot part from the mold. In this case, we have an underfill, which means that our mold did not fill completely. There are some usable parts, but not all of the parts are usable.
When we had 6, we were having a lot harder time. When we just inject 2, it's a lot easier for the melt.
This can be due to many factors such as barrel and nozzle temperature, mold temperature, injection time, injection pressure, too little material in the material chute, cycle time, and or time between injection events. We'll try again. We wait a minute or two for the material to heat up in the barrel. We repeat the same process as before, but this time the injection pressure will be increased. In the end, we have an overfill, which results in flash around the parts. Flash is the extra material that crept into the mating surfaces of the mold. There are some usable parts, but again, not all of them are usable. This can be due to many factors such as barrel and nozzle temperature, mold temperature, injection time, injection pressure, and or the cycle time. We will now repeat the process with the proper injection pressure. For this mold, an injection pressure of about 60 to 65 psi on the green gauge works very well. This time, we get a full fill in the mold.
6,500.
This is what we want to try to accomplish on every injection cycle.
All right, so everybody's going to get a chance to do that this week
Here
with
we
their
see our
partners
finished
and
parts.
teams of 2.
Each part will snap off the runner in which it's connected to. These parts are ready for post-machining.
Awesome. So let me go here real quick. So what we're going to do this week is after you injection mold them, go back over here, you're going to go ahead and cut them off the runners like Brian talked about. You're going to put it in a collet. We're going to hold it in a collet holder. We're going to drill and tap it. That's going to actually set up the datum. So if we go ahead and look over here, we injection mold the part, then this threaded hole, this 1/4-20 hole ends up being our datum. So we're making that datum on the lathe. We're then going to hold it by that datum and check the run out to see if we have more than 30 thou run out. So run out's the wobble motion based off rotating it about its datum, its central axis of rotation, which is going to be that thread. So we're going to rotate it about the thread we manufactured and see how wobbly it is so you can understand how run out works and basically it's another geometric dimensioning and tolerancing call out. So we'll learn all about run out and total run out this week. So hopefully you learned a little bit about injection molding. And I hope you enjoy lab this week. We're gonna make our parts, and then we'll come back next week and go do a laser cutting lab. So have a great week. Talk to you later. Bye.